So in this lesson, we are going to talk about two main things. We learned in lesson one about buffers. We're going to go into that a little bit more in depth and talk about how to prepare a buffer. And then we're also going to learn a new type of calculation that's similar to rice table calculations in some ways, but they're called BCA tables. So let's talk about preparing a buffer. So first of all, you have to find a table of weak acids and weak bases. And you want to find a weak acid or weak base that has a pKa value close to the desired pH. So the next thing you need to do is take the Henderson-Hasselbalch equation and rearrange it to find the correct ratio of conjugate base to acid that you need in order to maintain that specific pH.
That's high quality H2O.
Now, I mentioned this in lesson one, but just to re-emphasize it, that one of the nice characteristics about buffers is that it doesn't matter what volume you have. The quantity of water used does not matter because it's that ratio of conjugate base to acid that gives you the pH that is maintained. So diluting the buffer will not change the pH. If 100 mils of it is holding steady at a pH of 4.4, let's say, and I dilute that to 1 liter, then it's still going to hold steady at a pH of 4.4. Now, what does change is what we talk about in the next bullet.
Alrighty then.
So if you dilute it, it still maintains the same pH, but its capacity to neutralize any sort of invading acid or base goes down when you dilute it. Okay. So here's an example. Suppose you wish to prepare a buffer at a pH of 4.3. How would you proceed? Well, as we said, the first thing you need to do is you need to choose which weak acid you want to work with. So you choose a weak acid with a pKa that's close to the desired pH. So this is a condensed table. You have this on your handout. And so let's say that we have to choose between these three possible acids. I want to choose the one that has a pKa closest to my desired pH, which in this case is 4.3. And so obviously that means that you're going to need to calculate the pKa of all of these weak acids. And so if you remember, hopefully you remember that the pKa, okay, is equal to the negative log of the Ka. So that's how you would determine that. You got to take the negative log of each one of these and figure out which one has a pKa that's closest to your desired pKa of 4.3. All right, and if you do that, you'll find out that acetic acid is the one that you would choose because its pKa is closest to 4.3. Its pKa turns out to be 4.74. All right, so acetic acid is the best choice. So, as we said, what you do is you're going to rearrange the Henderson-Hasselbalch equation to find the ratio that gives you the desired pH. But we're going to go ahead and plug in what we know already. So we know already that I want to maintain a pH of 4.3. I know that since I'm using acetic acid as the basis for my buffer, it has a pKa of 4.74. So if I subtract 4.74 from both sides, right, just to move that over and collect terms, then what you end up with is Yahoo! Negative 0.44 on one side and the log of the conjugate base, which in our case is acetate from sodium acetate probably, or potassium acetate, and over the concentration of acetic acid, right? So remember what this means or how to interpret this. What this effectively means is that 10 raised to the power of negative 0.44 is equal to that ratio, okay, is equal to that ratio right there. Okay, because this is a log base 10, and this is the exponent you would put on the base 10 to get this number, whatever it might be. Okay, so 10 raised to the power of negative 0.44 is that ratio. And so if you plug that into your calculator, what you'll see in your calculator is just this number right here, 0.363. But remember that any number divided by 1 is itself. So effectively what we're saying is that as long as we maintain this ratio of 0.363 moles of the acetate for every 1 mole of acetic acid, then I will have a buffer that gives me that pH of 4.3 that I'm looking for. So this is that ratio of the conjugate base acetate to the weak acid, acetic acid, that you need to come up with.
All too easy.
So all you do is you just make your solution with this mole ratio. You weigh out, 0.363 moles of sodium acetate, and you dissolve it in 1 mole of acetic acid, or use solution stoichiometry to come up with a volume that gives you 1 mole of acetic acid, and you mix the two together, and it will be a buffer that maintains a pH of 4.3. Okay, so now what I'd like for you guys to do is to try this small group practice problem on your own. So pause the video, work on it, and then we'll talk about the solution. So in this problem, you were asked what ratio of ammonia to ammonium is required to prepare a pH buffer a buffer that maintains a pH of 9. And you're given the Ka for the ammonium ion, and you're given the Henderson-Hasselbalch equation. So this is very similar to the one that we just did. The first thing we might want to do is calculate the pKa, because that's pretty simple. So that's just the negative log. Negative log. So that's just the negative log of 5.6 times 10 to the minus 10. Okay, that's the pKa. All right, because that's what we're going to substitute in right there. And then the pH of 9, so that's going to be 9.00. And then we'll just rearrange again, set the difference as an exponent on 10 so that we can determine what this ratio is and then work from there. Okay, so the pH is 9, and that equals the negative log of the Ka plus the log of ammonia is the base and ammonium is the acid.
Yahoo!
So that difference, if you do the math here, that difference is a negative 0.25. So what that means is 10 raised to the power of negative 0.25 is that ratio of ammonia to ammonium. And then if you plug that into your calculator, again, what you'll see is that you get 0.56. So that's the mole ratio that you want. For every 0.56 moles of ammonia, you want to have 1 mole of ammonium. And if you make a solution with that ratio of these two things, then you will maintain a pH of 9.0. Okay, so now what we want to talk about is we're going to do some calculations that essentially prove that buffers work. And the way it's done is with something called a BCA table. So this bullet here says what or all of these bullets kind of lay out what we're going to do. So remember that the change of pH of a buffer is minimal, but it can be calculated, and we're going to use a table to organize the given information. That's called a BCA table. Now, I know that students will often confuse this with rice tables because we spend a lot of time talking about rice tables and emphasizing that technique for solving problems. But the BCA table is completely different than a rice table. It's used in different situations. It's only used with buffers and to calculate changes in the pH of a buffer. And as you'll see when we start doing it, it's fundamentally different in terms of what goes into the table. It's different than what we did with rice tables. Okay, so this is a similar technique to rice tables, but fundamentally different because they don't involve, first of all, reversible reactions and chemical equilibrium. All right, so we call these BCA tables. So what do the B and the C and the A stand for? Well, it's kind of a before, change, and after setup, as you'll see when we do this example next. Okay, so here's our example question. What is the pH? It's got 2 parts to it. And as you'll see, the 2 parts to this question are to kind of show you how a buffer works and that it does work at maintaining a steady pH. So part A, what is the pH of a solution if you add just 1 milligram of sodium hydroxide to 100 mils of water? And then we're going to do the same sort of thing to a 100 ml solution of a buffer made with acetic acid and sodium acetate that's maintaining a pH of 4.3. So we're going to take 100 mils of that solution, that mixture, and we're going to add 1 milligram of sodium hydroxide to that. Okay, so part A first. What is the pH of a solution made with 1 milligram of sodium hydroxide plus 100 milliliters of water? Okay, so the first thing we need to do really is we need to calculate how many moles of sodium hydroxide we're adding to this sample of water. And so that's just converting mass into moles. So I know that 1 milligram of sodium hydroxide, first of all, I need to change that into grams. And I know that 1 gram of NaOH is 1,000 milligrams of NaOH. So milligrams of sodium hydroxide cancel, and I have grams of sodium hydroxide. Okay, well, if you add up from the periodic table the average atomic masses of sodium, oxygen, and hydrogen, you'll see that 1 mole of sodium hydroxide is 40.0 grams of sodium hydroxide. 23 plus 16 plus 1. So units of grams of sodium hydroxide cancel, and right now I have moles of sodium hydroxide. Okay. All right, so punch that into your calculator, but I'm going to let PowerPoint do that. And you get 2.5 times 10 to the minus 5 moles of sodium hydroxide. Now, the next thing we need to do is we need to calculate the concentration of hydroxide ions that are in the solution, because that's going to be what determines the pH. Okay, because remember that sodium hydroxide, it's a strong base, so when you dissolve it in water, 100% is going to break apart into its component ions. So you get sodium ions, aqueous, and you get hydroxide ions, aqueous. Okay, so if I have 2.5 times 10 to the minus 5 moles of sodium hydroxide, then that means that I also have 2.5 times 10 to the minus 5 moles of hydroxide ions, all right? And so this is what we're going to divide by the volume to get a concentration. So if I divide that by 100 milliliters, but remember that the volume needs to be in liters, so I can make that conversion. 1,000 milliliters is 1 liter, right? So milliliters over milliliters cancel. So now I've got units of moles per liter, all right? And so that gives me a molarity of sodium hydroxide. So that's going to give me some units of molarity of this sodium hydroxide solution, or you could think of it in terms of the hydroxide ion solution, right? Okay, so if you divide that concentration by, that number of moles by the volume in liters, you get a molarity. So remember that this is also the molarity of the concentration of hydroxide ions. And I remember that the pOH is just the negative log of the hydroxide ion concentration. So that's going to be the negative log of 2.5 times 10 to the minus 4. Okay, and then I remember that in order to answer the question, what is the pH? I remember that the pH is just 14 minus the pOH. Okay, so you take the negative log of the 2.5 times 10 to the minus 4, and you get 3.6 as a pOH. And so then the pH is 14 minus 3.6, so you get a pH of 10.4. Okay, so the thing to notice is that we know that, before I put the sodium hydroxide into this water, it has a pH of 7. It's pure neutral water. But then I add just one tiny little speck, basically, of sodium hydroxide, a milligram. It would be on your finger, it would just like a little speck, like a little flake, small amount. That causes the pH to increase up to 10.4. Okay, so that change in pH is pretty big for such a small amount of solute. So if you needed to avoid drastic changes in pH, you would want some sort of buffer solution to deal with the addition of a tiny amount of sodium hydroxide. So pure water isn't going to cut it, because that causes that pH to jump so much. Think of it this way. You could drink easily 100 milliliters of water. That's a good thing to do. But you certainly wouldn't want to drink 100 milliliters of something that had a pH of 10.4. It would not be good for your esophagus. All right, so just that little speck of sodium hydroxide could cause something that's perfectly healthy to become something that's not good for you. Okay, so that's part A. So now we're going to move on to part B, and you'll see that we are going to use some of that information that we calculated in part A to do part B as well. So it says, what is the new pH of a 100 milliliter sample of acetic acid and sodium acetate buffer, which has a pH of 4.3, if, once again, 1 milligram of sodium hydroxide is added to the sample? Okay, so let's answer some questions before we launch really into calculating things. First of all, which component of this buffer, you got two components to this buffer, which one will react with the sodium hydroxide? So if the sodium hydroxide that I add is placed in this buffer, which one of these two things is going to react with it? Well, sodium hydroxide is a base, so it's going to react with the acid. So which one of these two things is the acid? It is the acetic acid. Okay, so that's going to be the component of the buffer that neutralizes that invading base. The acetic acid does that. Okay, so then it's also important to understand the reaction that occurs between acetic acid and the sodium hydroxide. So what would that reaction be? Thinking about what happens, we have the acetic acid, and it will react with sodium hydroxide. And remember, this is just one way to have a double displacement reaction. So the hydrogen will go to the hydroxide and the sodium goes to the acetate. They just switch partners. So your two products are going to be sodium acetate and water. Okay, and this is a strong reaction. This reaction occurs 100% because this is a strong base. So the acetic acid neutralizes the sodium hydroxide to give us sodium acetate and water. And as I said, this is a 100% reaction since it involves a strong base. So the next thing we need to do is we need to calculate the moles of each compound except water because it's the solvent. So it's not going to change its number of moles appreciably. So we're going to calculate the number of moles of each compound that are present before this reaction occurs. So now's where we're starting to gather some data to put into our table. Remember that the B in BCA stands for before. So that's really what we're going to calculate now. So how many moles of each compound except water are present before this reaction occurs? All right, well, if you remember from a few slides ago, we said that the concentration of this acetate, the C2H3O2 minus, over the concentration of acetic acid was equal to 0.363 to 1. Okay, well, to calculate the number of moles, these were molarity values, right? They're concentrations, which is moles per liter. So if I just multiply each one of these, this is in moles per liter, moles per liter. So if I multiply this times the volume of this particular sample, so this is a 100 milliliter sample, which is 0.1 liters. So 0.1 liters, liters over liters cancel, and you get 0.0363 moles of acetate. Okay, or you could also think of that as sodium acetate, right? That's the compound that gives you the acetate ion. And we do the same thing for the acetic acid. So multiply that times the sample volume. Okay, liters over liters cancel. So that gives you 0.100 moles of acetic acid. Okay, and I calculated in the previous slide, how many moles of sodium hydroxide. So the moles, just to refresh our memory, the moles of sodium hydroxide that we calculated in part A was 2.5 times 10 to the minus 5. Okay, so now I've got the number of moles of the three components before any reaction occurs. So from the earlier example, we know that if I'm going to maintain a pH of 4.3, that mole ratio needs to be 0.363 to 1, but those are concentrations. So we're only working with 0.1 liters. So what we do is we multiply each concentration by 0.1 to get the moles of each component. So that's 0.0363 moles of the sodium acetate. That's 0.1 moles of acetic acid. And again, we recall from part A that the moles of the sodium hydroxide is 2.5 times 10 to the minus 5. So now what we're going to do is we're going to organize this information in this, what we call BCA table. Okay, so the skeleton of the table is already printed in your handout there. So remember what the B and the C and the A stand for. The B stands for the number of moles. The only things you can put in your BCA table are moles. You don't put molarities, which is different than the rice table. That's one of the big differences. In a rice table, we put concentrations, but in a BCA table, you only put moles. Matter of fact, let me write that down, and you can put it in your notes. So only moles go in BCA tables. Okay, so that's one difference between BCA tables and rice tables. The other one we already mentioned. Rice tables involve reversible reactions, equilibrium systems. The reaction that we're going to work with here is not a reversible reaction. It's a 100% one-directional reaction. Okay, and there it is. Remember that the reaction that we're going to track is that reaction of the acetic acid, because it's going to be the component of the buffer that reacts with the sodium hydroxide that's being added. And the product is going to be the other component in our buffer, sodium acetate, and the water. Of course, the reason why this is blacked out is because we're not really, this, you know, it's just for completion, for the sake of being complete. We're not really going to numerically track how its number of moles changes. So in the previous slide, we actually generated numbers, which you can put in your row for before right here. So we said that we had 0.1 moles of acetic acid, 2.5 times 10 to the minus fifth moles of the sodium hydroxide, and 0.0363 moles of the sodium acetate. So that's before any reaction occurs. But we know that there is going to be a reaction. These two things are going to react with each other. This is a strong base. This is an acid. They're going to undergo a neutralization reaction. And so now we need to think about, well, what's the change going to be? How much of these things are going to react? Well, like I said, this is a 100% reaction. All of this sodium hydroxide is going to go away. So what I'm going to do is the change for sodium hydroxide is going to be a negative 2.5 times 10 to the minus 5. And since that sodium hydroxide reacts with acetic acid, then you have the same change in your acetic acid amount. This also changes by a minus 2.5 times 10 to the minus 5. Okay? So as I said, all of this is going to go away. It's a 100% reaction, so I'm going to lose all of that sodium hydroxide. Well, when that happens, I also lose an equivalent amount of acetic acid because the two react with each other. So I'm going to lose 2.5 times 10 to the minus 5 moles of acetic acid. Now, think about how the sodium acetate amount changes. Well, when this reacts with this, it produces this. So if I lose this amount of these two reactants, then I gain that amount of sodium acetate as a product. Okay, so it's the same number, but it's positive. And then after, you just, like another similarity with the rice tables, you just add up your columns. Okay, so I'm going to lose 2.5 times 10 to the minus 5 moles of acetic acid and sodium hydroxide, and I gain 2.5 times 10 to the minus 5 moles of sodium acetate. And so after, we get these numbers. So of course, we're going to end up with 0 amount of sodium hydroxide. It's the limiting reactant. All of it gets neutralized. And I change the amount of acetic acid just a little bit. It doesn't change by that much. And I increase the amount of sodium acetate. Again, not by much. It's still 0.0363, but I just tack on the 2.5 at the end. And I just, subtracted the 2.5 times 10 to the minus 5 from the acetic acid. Okay, but the key here is that now I have different amounts to plug into my Henderson-Hasselbalch equation in order to calculate the new pH. Remember, that's what the Henderson-Hasselbalch equation is for. That's what it does. It calculates pH. So originally, when we used the Henderson-Hasselbalch equation and the numbers that we were given, we had a pH of 4.3. And so let's see, using these numbers, these after numbers, how that affects the pH. So I use Henderson-Hasselbalch. I plug in the numbers that I have from the, well, of course, the pKa is still the same, but new numbers from the BCA table. Okay, so you get now these two numbers, and lo and behold, you plug all that into your calculator, you see that you still get a pH of 4.3, which is unchanged. Okay, so we'll stop there. And so based on what we've learned today, you should be able to do number 3 in your homework assignment. And then in the extra practice assignment, there are 2 questions that have to do with BCA tables and how and calculations involving buffers that maintain a steady pH, maybe not, an unchanged pH, but a steady pH. And then again, some good tutorial videos for you to take a look at.